Welcome to our lecture series on thermodynamics and the properties of matter. In this first batch, we are diving into Chapter 3, which covers the fundamental gas laws. We will explore how pressure, volume, and temperature interact to dictate the behavior of gases. Let's begin with Boyle's law. This fundamental principle states that for a fixed mass of gas at a constant temperature, the pressure is inversely proportional to its volume. Mathematically, pressure times volume equals a constant, which gives us the highly useful working equation, P1V1 equals P2V2. To verify Boyle's law experimentally, we can use a J-tube apparatus. We trap a fixed mass of air using mercury. By raising or lowering the open end of the flexible tube, we change the pressure on the trapped air. We record the atmospheric pressure, H, the difference in mercury levels, H, and the length of the air column, L. The total pressure, P, is H plus or minus H. Once we have our measurements, we repeat the procedure to get a series of values for pressure and length. Since the tube has a uniform cross-section, the length of the air column is directly proportional to its volume. Plotting pressure against 1 over length yields a straight line passing through the origin, perfectly verifying Boyle's law. Let's look at a practical example. If a gas has a volume of 100 cubic centimeters at a pressure of 75 newtons per square meter, what happens when we compress it to 60 cubic centimeters? Using P1V1 equals P2V2, we plug in our values and solve for P2, finding that the new pressure increases to 125 newtons per square meter. Moving on to Charles' law, this law states that the volume of a fixed mass of gas is directly proportional to its absolute temperature, provided the pressure remains constant. This means that as a gas heats up, it expands. The working equation here is V1 over T1 equals V2 over T2. When discussing temperature in these gas laws, we must always use absolute temperature, measured in Kelvin. Absolute zero, or 0 Kelvin, is the theoretical temperature attained when molecules slow down and acquire their absolute minimum possible energy. Let's look at the molecular explanation for absolute zero. As a gas cools, its molecules lose kinetic energy. They slow down and move closer together. Eventually, if cooled enough, they would theoretically cease to have kinetic energy entirely. At this point, the gas occupies a negligible volume and exerts negligible pressure. This state defines absolute zero. Here's an application of Charles' law. A gas at 0 degrees Celsius has a volume of 75 cubic centimeters. We heat it to 273 degrees Celsius. Notice we must convert Celsius to Kelvin by adding 273. Plugging these absolute temperatures into our equation, we find the new volume doubles to 150 cubic centimeters. The third foundational gas law is the pressure law, also known as Gay-Lussac's law. It states that the pressure of a fixed mass of gas is directly proportional to its absolute temperature, as long as the volume is held constant. The formula is P1 over T1 equals P2 over T2. Let's calculate a new pressure using Gay-Lussac's law. A gas at negative 73 degrees Celsius has a pressure of 75 newtons per square meter. We heat it to 127 degrees Celsius. After converting both temperatures to Kelvin, we solve for P2, which comes out to 150 newtons per square meter. In reality, pressure, volume, and temperature often change simultaneously. By combining Boyle's, Charles', and the pressure laws, we get the equation of state. This combined gas law states that P1V1 over T1 equals P2V2 over T2. Let's see how the equation of state handles simultaneous changes. We have 1 cubic meter of gas at negative 73 degrees Celsius. We triple the pressure, and the temperature rises to 27 degrees Celsius. By setting up our equation, the initial pressure P cancels out, allowing us to solve for the new volume, which is 0.5 cubic meters. Often in physics and chemistry, you will see the abbreviation STP, which stands for Standard Temperature and Pressure. This is a universally agreed upon reference point, where the absolute temperature is 273 Kelvin, and the pressure is 76 centimeters of mercury. Now, let's formally derive the ideal gas equation. Imagine a fixed mass of gas. First, we warm it at a constant pressure, applying Charles' law to find the intermediate volume. Then we compress it at a constant temperature, applying Boyle's law. Substituting the intermediate volume links all three variables, proving that P times V over T is a constant. This constant is proportional to the number of moles, giving us PV equals nRT. This brings us to the famous ideal gas equation, PV equals nRT. Here, N represents the number of moles of the gas, which is the given mass divided by the relative molecular mass. R is the universal molar gas constant, which has a value of 8.31 joules per mole per Kelvin. Next, we introduce Dalton's law of partial pressure. If you have a mixture of gases that do not react chemically, the total pressure is simply the sum of the individual partial pressures. The partial pressure is defined as the pressure a single gas would exert if it occupied the entire container by itself. We've mentioned ideal gases several times, but what exactly defines one? An ideal gas obeys Boyle's law perfectly under all conditions. Its properties include having internal energy that is entirely kinetic, negligible intermolecular forces, negligible molecular volume, perfectly elastic collisions, and instantaneous collision durations. When a gas expands, it does work on its surroundings. Imagine a gas pushing a frictionless piston of area A outward by a distance dx. The force is pressure times area. Work is force times distance, which simplifies to pressure times the change in volume. Integrating this gives us the total external work done. W equals P times delta V. This brings us to the first law of thermodynamics, which is the law of conservation of energy applied to thermal systems. It states that the heat supplied to a system, delta Q, equals the increase in its internal energy, delta U, plus the external work done by the system, delta W. We can substitute P delta V for the work done. Unlike solids and liquids, gases have two distinct specific heat capacities depending on the conditions. We have specific heat capacity at constant volume, denoted by a lowercase cv, and at constant pressure, denoted by a lowercase cp. We also define molar heat capacities, denoted by capital CV and Cp, which measure the heat required per mole instead of per kilogram. There is a fundamental relationship between the molar heat capacities. Using the first law of thermodynamics, we can express the heat supplied at constant pressure and at constant volume. By substituting the ideal gas equation for the work term, we find that the molar heat capacity at constant pressure is exactly equal to the molar heat capacity at constant volume plus the universal gas constant R. You might wonder why the heat capacity at constant pressure is always greater. It's because when you heat a gas at constant pressure, it expands, doing external work. The heat supplied must cover both the increase in internal energy and this external work. At constant volume, no work is done, so all heat goes purely into internal energy. The ratio of these two capacities is denoted by the Greek letter gamma. Let's classify thermodynamic processes. An isovolumetric process occurs at a constant volume, meaning no external work is done. An isobaric process occurs at a constant pressure, typically in a cylinder with a movable piston, where the work done is the pressure multiplied by the change in volume, which is the area under a pressure-volume graph. An isothermal process is one where the temperature remains perfectly constant. Because the temperature doesn't change, the internal energy of an ideal gas remains constant as well. According to the first law of thermodynamics, this means any heat supplied to the gas is entirely converted into external work. In contrast, an adiabatic process involves absolutely no heat exchange with the surroundings. Because delta Q is zero, any external work done by the gas must come at the expense of its own internal energy. This is why a gas cools down when it expands adiabatically. Moving into Chapter 4, we encounter the kinetic theory of gases. This theory is grounded in observations like Brownian motion, which is the random, haphazard movement of particles. The kinetic theory states that matter is made of molecules in continuous motion, and their speed is directly proportional to the temperature. To wrap up this batch, let's look at how we correct the ideal gas law for real-world gases. The van der Waals equation introduces two corrections. It accounts for intermolecular forces by adding the pressure defect term, and it accounts for the physical volume of the molecules by subtracting a co-volume term. This gives us a much more accurate model for real gases. We will continue exploring the behavior of vapors and liquids in the next part of our series. Moving right into the kinetic theory of gases, let us consider why the pressure of a fixed mass of gas rises when its temperature is increased at a constant volume. A gas consists of molecules that are free to move in all directions because their intermolecular forces are negligible. As these molecules move, they collide with each other and the walls of their container. It is these collisions with the walls that create what we measure as pressure. When the temperature of the gas increases, the average kinetic energy of the molecules also increases. Because they are moving faster, they hit the walls more frequently. Additionally, each collision involves a higher rate of change of momentum. Both of these factors combine to result in a greater overall pressure. Now, what happens if we keep the temperature constant but decrease the volume? When the volume occupied by the gas is reduced, the physical distance between the walls of the container is shorter. Because the temperature is constant, the molecules are moving at the same average speed, but they now take less time to travel from one wall to another. This means the number of collisions per unit time, per unit area of the wall, increases. More frequent collisions over a smaller area directly translate to an increase in pressure. To mathematically describe this pressure, we derive the expression P equals 1/3 rho c squared. Before we do the math, we must establish 4 key assumptions of the ideal gas model. First, intermolecular forces of attraction are considered negligible. Second, all collisions the molecules make are perfectly elastic, meaning no kinetic energy is lost. Third, the actual volume of the molecules themselves is negligible compared to the total volume of the container. And fourth, the duration of a collision is negligible compared to the time spent traveling between collisions. Let us begin the derivation. Consider a single molecule of mass m moving inside a cubic container of side length L. Suppose it is moving towards a wall with a velocity u. When it hits the wall and bounces back elastically, its velocity becomes negative u. The change in momentum is the final momentum minus the initial momentum, which gives us 2mu. The time it takes for the molecule to travel back and forth across the cube between collisions with the same wall is the total distance, 2L, divided by its velocity, u. Therefore, the rate of change in momentum is 2mu divided by this time t. According to Newton's second law, the rate of change of momentum equals the force exerted. Substituting our time expression, the force F1 exerted by a single molecule is mu1 squared divided by L. But a gas contains many molecules. For n molecules, the total force F on the wall is the sum of the individual forces, mu1 squared over L plus mu2 squared over L, all the way to molecule n. To find the pressure P, we divide this total force by the area of the wall, which is L squared. This gives us pressure equals m over L cubed, multiplied by the sum of the squared velocities of all n molecules. Writing out the sum of all those squared velocities is cumbersome, so we use the mean square velocity, denoted as capital U squared. This is simply the sum of the squared velocities divided by the total number of molecules, n. Rearranging this, the sum of the squared velocities equals n times u squared. Substituting this back into our pressure equation, we get P equals n times m times u squared divided by L cubed. Notice that n times m is the total mass of the gas, and L cubed is the volume. Mass divided by volume is density, rho. So the pressure P simplifies to rho times u squared. We are almost there. So far, we only considered motion in one direction, u. But molecules move randomly in 3 dimensions, with velocities u, v, and w. The overall mean square speed, c squared, is the sum of u squared, v squared, and w squared. Because motion is random, there's no preferred direction, meaning u squared equals v squared equals w squared. Therefore, c squared equals 3 times u squared, or u squared equals 1/3 c squared. Substituting this into our previous equation gives the final expression, pressure P equals 1/3 rho c squared. By replacing density with total mass, mm, over volume v, we can also write this as PV equals 1/3 mmc squared. Now let us connect this mechanical view of a gas to thermodynamics. We have our kinetic theory equation, PV equals 1/3 nmc squared. We also have the ideal gas equation from macroscopic observations, PV equals nRT, where n is the number of moles and r is the gas constant. Since both equal PV, we can equate them. 1/3 nmc squared equals nRT. By multiplying both sides by 3 and dividing by n, we isolate mc squared, which equals 3 nRT over n. To find the kinetic energy, we multiply both sides by 1/2. This gives us 1/2 mc squared equals 3/2 nRT over n. For 1 mole of gas, the number of molecules n equals Avogadro's constant, n subscript a. The ratio of the universal gas constant, R, to Avogadro's constant is known as the Boltzmann constant, K. Thus, the mean translational kinetic energy of a single molecule, 1/2 mc squared, simplifies beautifully to 3/2 kT. This is a profound result. The mean kinetic energy of gas molecules is directly proportional to the absolute temperature. Consequently, the root mean square speed is directly proportional to the square root of the absolute temperature. Let us apply these concepts with an example. We need to calculate the root mean square speed of methane molecules in Jupiter's atmosphere, where the temperature is -130 degrees Celsius. First, we convert the temperature to Kelvin by adding 273, giving 143 Kelvin. We use the formula derived earlier, relating C squared to temperature and molar mass. The molar mass of methane is 16.04 grams per mole, which we must convert to kilograms. Plugging in the gas constant, temperature, and molar mass, we find the RMS speed is 4.71 times 10 to the power of 2 meters per second. The problem states the speed of sound is a factor of 0.682 of this RMS speed, which calculates to 321.2 meters per second. In our second example, we are given the density of oxygen as 0.098 kilograms per cubic meter at a pressure of 1.0 times 10 to the 5 newtons per square meter. We need to find the root mean square speed. This is a direct application of our pressure equation, P equals 1/3 rho c squared. Rearranging for the RMS speed, we get the square root of 3p over rho. Substituting the given pressure and density values into the equation yields an RMS speed of 1749.64 meters per second. Example 3 asks for the RMS speed of an ideal gas at 130 degrees Celsius, given its density and pressure at 0 degrees Celsius. First, we calculate the RMS speed at 0 degrees Celsius, or 273 Kelvin, using the square root of 3p over rho. This gives us the initial speed. Then, we use the principle that the RMS speed is directly proportional to the square root of the absolute temperature. We set up a ratio. RMS speed 1 over RMS speed 2 equals the square root of T1 over T2. Plugging in our initial speed, 273 Kelvin for T1, and 403 Kelvin for T2, we solve for the new RMS speed, which is approximately 556.5 meters per second. Example 4 follows a very similar logic. We need the RMS speed of hydrogen at 27 degrees Celsius, knowing its density at 0 degrees Celsius. Again, we first find the square of the speed at 0 degrees Celsius using 3p over rho, which gives 3.333 times 10 to the 6th. Then we use the temperature proportionality ratio. We compare the square root of the initial squared speed to the unknown final speed, equating it to the square root of 273 Kelvin over 300 Kelvin. Solving this ratio gives the final RMS speed of hydrogen at 27 degrees Celsius as 1.91 times 10 to the 3 meters per second. Here are the first 3 problems from exercise 39 for you to practice. Problem 1 is a straightforward application of the RMS speed formula using standard temperature and pressure. Problem 2 asks you to calculate the molar gas constant, the Boltzmann constant, and the average translational kinetic energy for a mole of gas, testing your understanding of the relationships between macroscopic and microscopic constants. Problem 3 combines the ideal gas law to find the mass and number of atoms of helium in a vessel, followed by calculating the RMS speed. The answers are provided for you to check your work. Moving on to problems 4 through 6. Problem 4 introduces the concept of total kinetic energy and asks you to determine the specific heat capacity at constant volume by comparing the kinetic energy at 2 different temperatures. Problem 5 requires calculating the mass and internal energy of helium, reinforcing that internal energy for an ideal gas is solely its translational kinetic energy. Problem 6 is a comprehensive exercise using uranium hexafluoride, asking for moles, mass, density, and RMS speed, requiring you to synthesize several of the formulas we have derived. Finally, problems 7 through 10. Problem 7 is particularly conceptual. After calculating the initial state, you must explain how an isothermal expansion affects internal energy, RMS speed, and density. Remember that temperature dictates kinetic energy. Problem 8 is a direct high-temperature RMS calculation. Problem 9 is another full-state calculation for oxygen. And Problem 10 compares the RMS speeds of helium and hydrogen at the same elevated temperature, highlighting how molar mass affects molecular speed. Take your time to work through these to solidify your understanding. Now we will see how the kinetic theory successfully deduces the empirical gas laws, starting with Boyle's law. Boyle's law states that for a fixed mass of gas at a constant temperature, pressure and volume are inversely proportional, meaning P times V is a constant. Starting from our kinetic theory equation, PV equals 1/3 nmc squared, we multiply both sides by 1/2 to reveal the kinetic energy term, 1/2 mc squared. We know this kinetic energy is directly proportional to temperature. If the temperature is constant and the number of molecules n is constant for a fixed mass, then the entire right side of the equation is constant. Thus PV equals a constant, proving Boyle's law. Next is Charles' law, which states that volume is directly proportional to absolute temperature at a constant pressure. We start with the same modified equation. 1/2 PV equals 1/3 N times the kinetic energy, 1/2 mc squared. This time we rearrange the formula to make volume, V, the subject. We get V equals 2 over 3 np, multiplied by the kinetic energy. Since the kinetic energy is proportional to temperature T, and we are holding pressure P and the number of molecules N constant, all other terms are constants. Therefore, volume is directly proportional to temperature, exactly as Charles' law dictates. The kinetic theory also explains Dalton's law of partial pressures. This law states that the total pressure of a non-reacting gas mixture is the sum of the partial pressures of its components. Using PV equals 1/3 nmc squared, we can express the number of molecules N as 3 PV over mc squared. For a mixture of two gases in the same volume V, the total number of molecules N is N1 plus N2. Substituting our expressions for N, N1, and N2, we get an equation with pressure and kinetic energy terms. Because the mixture is at thermal equilibrium, the average kinetic energies of all gas types are equal. Canceling out the volume and kinetic energy terms leaves us with the total pressure P equals P1 plus P2. Up to this point, we have relied on the assumptions of an ideal gas. However, real gases only obey the ideal gas equation, PV equals nRT, under specific conditions, very low pressure and high temperatures. Real gases differ from the ideal model in several key ways. First, their intermolecular forces of attraction and repulsion are not negligible. Molecules do interact. Second, the physical volume of the molecules themselves is not negligible compared to the container's volume. Third, collisions between molecules are not perfectly elastic, meaning some energy is dissipated. Because of these factors, real gases do not perfectly obey the standard gas laws. So why do real gases behave ideally at high temperatures and low pressures? At high temperatures, the molecules have a very high average kinetic energy and move faster. This increased energy overcomes intermolecular forces, and the separation between molecules increases, making those forces effectively negligible. On the other hand, at low pressures, the gas is allowed to expand, meaning the total volume of the container increases significantly. When the container volume is massive, the actual physical volume taken up by the molecules themselves becomes a tiny, negligible fraction of the total space. Finally, let us look at the pressure-volume curve for a real gas compressed below its critical temperature. The graph is divided into three distinct regions. In region A to B, at lower pressures, the substance is an unsaturated vapor that fairly closely obeys Boyle's law, shown by the curve. As we compress it further into region B to C, the vapor begins to condense. Here, we have a mixture of liquid and saturated vapor, and interestingly, the pressure remains completely constant, even as the volume reduces. Once all the vapor has condensed, we reach region C to D. Here, we are compressing a liquid, which is highly incompressible, resulting in a very steep pressure spike for a tiny change in volume. In the next section, we will explore further implications of these phase changes and critical temperatures. Let us jump straight into the concept of vapors. A vapor is simply the gaseous state of a substance when it is below its critical temperature. If it is above that critical temperature, we call it a gas. We classify vapors into two main types, saturated and unsaturated. A saturated vapor is one that has reached a state of dynamic equilibrium with its own liquid, meaning the rate at which molecules evaporate equals the rate at which they condense. Because of this constant phase change, saturated vapors do not obey standard gas laws. On the other hand, an unsaturated vapor is not in equilibrium with its liquid and behaves much more like an ideal gas, meaning it approximately obeys the gas laws. When a vapor reaches that state of dynamic equilibrium, it exerts a specific pressure known as saturated vapor pressure, or SVP. This is the maximum constant pressure exerted by the vapor when it is in perfect balance with its liquid state. It is important to understand what drives this balance. The rate at which the liquid evaporates is strictly tied to its temperature. Meanwhile, the rate at which the vapor condenses back into liquid depends on how dense the vapor is. Ultimately, the saturated vapor pressure itself is dictated by the temperature. To truly understand SVP, we must look at it through the lens of kinetic theory. Imagine a liquid confined in a container with a fixed piston. The molecules in the liquid are moving randomly. The most energetic molecules near the surface have enough kinetic energy to break free from the attractive forces of their neighbors, escaping into the space above as vapor. This is evaporation. These newly formed vapor molecules also move randomly, colliding with the container walls to create pressure. Eventually, some of these molecules strike the liquid surface and are recaptured, which is condensation. When the number of molecules escaping exactly equals the number returning, dynamic equilibrium is achieved. At this exact point, the vapor pressure is at its maximum for that temperature. What happens if we push that piston down and change the volume while keeping the temperature constant? Initially, decreasing the volume compresses the saturated vapor, which increases its density. Because the vapor is now denser, the rate of condensation spikes. More molecules are forced back into the liquid phase than are evaporating. This continues until the density drops back to its original equilibrium level. Therefore, the dynamic equilibrium is restored, and the pressure returns to its exact original value. This is why saturated vapors do not obey Boyle's law. Changing the volume at a constant temperature has absolutely no permanent effect on the saturated vapor pressure. Now, let us see what happens when we change the temperature instead of the volume. If we heat the liquid, we increase the mean kinetic energy of its molecules. This causes a surge in the rate of evaporation. The space above the liquid quickly fills with more vapor molecules, increasing the vapor density. This higher density eventually forces the condensation rate to catch up until a new dynamic equilibrium is reached. But now we have more molecules in the vapor phase, and they are moving much faster. This results in a significantly higher pressure. Unlike unsaturated vapors, which increase pressure linearly with temperature, saturated vapor pressure increases almost exponentially. To verify this exponential relationship experimentally, we use a specialized setup. We place a liquid in a flask connected to a condenser, a thermometer, a mercury manometer, and a vacuum pump. First, we use the vacuum pump to set the pressure above the liquid to a desired value, then close the tap. We heat the liquid until it boils. At the boiling point, we record the temperature of the vapor. Simultaneously, we measure the difference in the mercury levels in the manometer, denoted as H. The actual vapor pressure is the barometric height H plus or minus this difference, H. By repeating this process at various pressures, we can collect a series of temperature and pressure data points. When we plot the data gathered from the experiment with SVP on the vertical axis and temperature on the horizontal axis, we get a distinct upward-sloping curve. This confirms our kinetic theory prediction. Saturated vapor pressure increases exponentially with temperature. Because of this complex, nonlinear behavior driven by continuous phase changes, you must never apply the standard ideal gas equation to saturated vapors. The combined gas law is strictly reserved for unsaturated vapors and ideal gases. In many physics problems, you will encounter a closed vessel containing a mixture of air and water vapor. If the vapor is unsaturated, you can treat the whole mixture as a gas. However, if the vessel contains a gas and a saturated vapor, you must use Dalton's law of partial pressures. Dalton's law states that the total pressure is the sum of the partial pressure of the dry gas and the saturated vapor pressure. Because the saturated vapor does not obey gas laws, you must subtract the SVP from the total pressure to find the pressure of the dry gas. Only then can you apply the ideal gas equation to the dry gas alone. Let us look at an example. A vessel has air saturated with water at 77 degrees Celsius with a total pressure of 1,000 millimeters of mercury. We cool it to 27 degrees. First, we isolate the dry air pressure at 77 degrees by subtracting the SVP of 314 from 1,000, giving us 686 millimeters of mercury. Since the volume is fixed, we apply the pressure law to the dry air. P1 over T1 equals P2 over T2. Remember to convert temperatures to Kelvin. Solving this gives us the new partial pressure of the dry air. Finally, we add back the new SVP at 27 degrees, which is 27, to find the new total pressure of 615 millimeters of mercury. In this second example, we need to find an unknown SVP at a higher temperature. We are given the total pressures at 20 degrees and 75 degrees. Crucially, the problem states some water remains liquid at 75 degrees, meaning the vapor is still saturated. We find the initial dry air pressure by subtracting the 20-degree SVP from the total pressure, giving 720. We set up our gas law equation for the dry air, leaving the final SVP as a variable, PS2, in the numerator. Solving the proportion yields the SVP at 75 degrees, which is 288.8 millimeters of mercury. Here we have air trapped in a tube by a drop of water. The drop ensures the trapped air is saturated. Because the tube is open to the atmosphere on one side, the total pressure inside equals atmospheric pressure, 760. We find the dry air pressure at 10 and 30 degrees by subtracting their respective SVPs from 760. Since the tube has a uniform cross-section, the volume of the gas is directly proportional to the length of the air column. We use the combined gas law, substituting length for volume, and solve for the new length, L2, which comes out to 11.15 centimeters. In our final calculation example, we cool a saturated mixture while maintaining a constant total pressure. A key insight here is that at 100 degrees Celsius, water is at its normal boiling point, meaning its SVP is exactly equal to standard atmospheric pressure, 1.01 times 10 to the 5 pascals. We subtract this from the total pressure to get our initial dry gas pressure. We do the same for the final state using the 20-degree SVP. Plugging these partial pressures, the initial volume, and the Kelvin temperatures into the combined gas law allows us to isolate and solve for the final volume. Moving from vapors to phase changes, let us examine boiling. Boiling is the process where a liquid turns into a vapor at a specific constant temperature. Microscopically, as you heat a liquid, you are giving the molecules more kinetic energy. They move faster and faster, pulling against the intermolecular forces holding them together. Boiling officially occurs when the saturated vapor pressure of the liquid grows large enough to exactly equal the external pressure pushing down on it. At this exact point, molecules throughout the entire bulk of the liquid, not just the surface, have enough energy to overcome atmospheric pressure and escape as vapor. Because boiling is entirely dependent on overcoming external pressure, changing that pressure changes the boiling point. If you increase the external pressure on a liquid, the liquid must reach a much higher saturated vapor pressure to boil. Since SVP only increases with temperature, the liquid must be heated to a higher temperature to boil. Conversely, if you climb a mountain, the atmospheric pressure drops. With less pressure pushing down, the liquid's SVP equals the external pressure at a much lower temperature, meaning water boils below 100 degrees Celsius at high altitudes. You may have noticed that once water starts boiling, a thermometer placed in it stops rising. Why does the temperature remain constant? Once the boiling point is reached, all the thermal energy you supply stops increasing the kinetic energy of the molecules. Instead, it is used entirely as latent heat to do the mechanical work of breaking the intermolecular bonds. The temperature will not rise again until the liquid has completely turned to vapor. Additionally, adding impurities like salt to water raises its boiling point. The impurities absorb some of the heat and disrupt the vapor pressure, meaning the water must get hotter than normal to boil, which actually helps cook food faster. While boiling happens throughout the liquid at a specific temperature, evaporation is a surface phenomenon that happens at all temperatures. According to kinetic theory, evaporation occurs when the most energetic molecules, those near the surface and moving in the right direction, break free into the air. Because only the fastest, highest energy molecules escape, the average kinetic energy of the molecules left behind drops significantly. Since temperature is a direct measure of average kinetic energy, this loss of high-energy molecules means the remaining liquid physically cools down. This is why evaporation is fundamentally a cooling process. If we want to speed up evaporation, we have 4 main methods. We can increase the surface area, exposing more molecules to the air. We can increase the temperature, giving more molecules the energy to escape. We can reduce the air pressure above the liquid, making it easier for molecules to break free. Finally, we can introduce a draft or wind, which blows away the escaped vapor molecules before they have a chance to condense back into the liquid. Remember the key distinctions. Evaporation happens only at the surface and at any temperature, whereas boiling happens throughout the entire volume, but only at one specific temperature. Let us shift our focus to the transition from solid to liquid, known as melting. Just like boiling, melting occurs at a specific, constant temperature for a given pressure. When you heat a solid at its melting point, the temperature stops rising. The thermal energy you are adding is no longer increasing the speed or kinetic energy of the molecules. Instead, the energy is doing work to weaken the rigid intermolecular forces, pushing the molecules further apart. This increases the potential energy of the system, while the kinetic energy stays flat, which is why the thermometer reading does not change until the solid has completely melted. The physics of melting explains some fascinating real-world phenomena. Take ice skating. As the blade moves, the work done against friction generates internal energy, melting a tiny amount of ice. This creates a thin film of water that acts as a perfect lubricant, allowing the skater to glide. Another classic example is a weighted wire cutting through a block of ice. The heavy weights create immense pressure directly under the thin wire. Because water expands when it freezes, applying pressure actually lowers its melting point. The ice under the wire melts, the wire drops down, and the water flows above the wire. Once above the wire, the pressure is gone, so the water immediately refreezes. The wire passes all the way through, but the block remains solid.
Evaporation and heat transfer dictate many everyday practices. If you wrap a milk bottle in a wet cloth, it cools much faster than if left bare. The water in the cloth evaporates, pulling latent heat away from the bottle and the milk inside. Similarly, when we sweat, our bodies are using evaporation to cool down. However, if a heavily perspiring person stands in a strong drought, the wind accelerates evaporation so rapidly that it can overcool the body, potentially lowering immune resistance. Also, using metallic utensils in a fridge is inefficient. Metals are excellent heat conductors. They hold on to the heat from the food, delaying the volatile refrigerant liquids from carrying that heat away to the cooling vents.
The sensation of cold is entirely about the rate of heat transfer from your body. Taking a cold bath on a hot, sunny day feels much colder than on a cool, rainy day. On a hot day, your skin temperature is high, creating a large temperature gradient with the water. The water rapidly absorbs a massive amount of heat from your body, triggering a strong sensation of cold. On a rainy day, your skin is cooler, the heat transfer is slower, and the shock is less. This same principle explains why a person suffering from a fever feels freezing when exposed to cold water. Their elevated body temperature causes heat to be stripped away by the water at a much faster rate than a healthy person. Water has a unique property. It expands when it freezes. This is why water bottles placed in a freezer are never filled to the brim, and why they are made of plastic rather than glass. The empty space allows the ice to expand, and the plastic can stretch slightly to withstand the internal pressure, whereas rigid glass would shatter. Another common water phase change is condensation on car windshields during a rainstorm. The cold rain chills the glass. When the warm, moist air inside the car hits that cold glass, the air's temperature drops below its dew point. It can no longer hold all its water vapor, which condenses into a cloudy film of liquid droplets on the screen. Let us look at a practical engineering solution to a physics problem, often tested in exams. On a high mountain, atmospheric pressure is low, so water boils at a much lower temperature, making it difficult to cook food thoroughly. How do we fix this? We use a pressure cooker. A pressure cooker is a sealed pot that traps the steam as the water heats up. This trapped steam dramatically increases the pressure inside the pot. The cooker features a calibrated safety valve that only opens when the internal pressure reaches normal sea-level atmospheric pressure, 76 centimeters of mercury. This guarantees the water inside must reach exactly 100 degrees Celsius before it can boil, ensuring your food cooks properly regardless of altitude. To wrap up our discussion on thermal physics and phase changes, remember these core principles. Saturated vapors are in a constant state of dynamic equilibrium and ignore standard gas laws, while their pressure, SVP, is dictated entirely by temperature. When dealing with mixtures, always use Dalton's law to isolate the dry gas before doing calculations. We saw that boiling is a bulk process dependent on external pressure, whereas evaporation is a surface phenomenon that actively cools the remaining liquid. Finally, during both boiling and melting, temperature remains perfectly flat because all added energy is used as latent heat to break molecular bonds. Keep these concepts in mind, and you will master thermal physics.